key component of derivatives and the things, it's one of the biggest applications that we have that we've done during the first half of the class. And so it's almost always in there. For sure in the multiple choice section there'll be some stuff about it. And oftentimes it's part of a free response question like this one. So it really is a key thing. There is even a connection back to parametrics a little bit if you want to think of it that way. Now we don't have to think about parametrics. I told you that wouldn't be on this test. But when they give you the velocity equation, they talk about it moving on the x-axis. Then they ask you about position. Now some of you call the position function p, some people call it s. I think a pretty good habit to get into when it talks about the position on the x-axis is to actually call the function x of t, because it does kind of connect us back to this idea of the parametric equation. Because if we have two-dimensional motion, this is just one-dimensional, just horizontal motion. Two-dimensional motion, we talk about a horizontal vertical component. We talk about parametrics, and we use x to be the horizontal component. So I think it's a nice way to do it, is to call it x of t, and they often do as well. Matter of fact, if you wanted to graph on your calculator a particle moving back and forth on the x-axis, you would go to parametric mode, and you would let x be the position function we're about to find here, and you'd let y be what? 0, right? Oh, I missed it. You'd let y be 0, because it has no vertical movement. And that would give you a picture of the particle just moving back and forth. Now, again, not necessary to do, but that would be something you could do. All right, well, anyway, to go from velocity to position, we do what? Antiderivative. So, and we're going to spend a lot more time on antiderivatives later, but a simple one like this could potentially be on the midterm test. So, antiderivative, that's t cubed. Antiderivative of 12t is 6t squared, and you can't forget the plus c. Now they also give you an initial condition. They tell you the velocity at a certain point, they tell you the particle is at this position. So in other words, they've told you x of 0 is -6. X of 0 is -6. So they've given you this position. It's really an initial value problem is what it is. If you think about it, what they gave you here with the velocity was x prime. Go back to parametrics. What did we call x prime and y prime? Those were the horizontal and vertical velocities. That's what this particle has, is horizontal velocity, because that's its only movement. So v is really like giving you x prime. So this is really a differential equation with an initial condition, an initial value problem is what this is. We do the antiderivative, be a type 1 differential equation. We can do the antiderivative, we plug in our initial condition, pretty easy to see when you put a 0 in that your output is going to be -6, so C is going to be -6 on this one. So there's your position function. Now you are supposed to write it with A, so you would have to write this as A cubed minus 6A squared minus 6 to answer part A. All right, write an expression for the speed. What did we say? We talked about this yesterday. How do you get, what's a speed equation? So your answer in part B could literally be S of t equals bars and then V of t. You wouldn't even have to write out the velocity equation. Since it had been defined earlier in the problem as V of t, you can use V of t in part of your answer to name that. That's good enough. That part B would be 1 point. I mean, you're either going to get it or you're not going to get it. There was nothing else to do for that. Okay? In what direction is a particle moving? What did you do for part C? There'd be several things you could do. Somebody got an idea? Do what with the velocity? That would be the one I would hope you would think about, because this is essentially a chart question. This is essentially a derivative equals 0 kind of a thing. Think of velocity as the derivative. We're trying to see when the particle is increasing, when is it decreasing. In other words, when's it going to the left? That'd be decreasing. When's it going to the right? That'd be increasing. That's a chart kind of question. Do the derivative, set equals 0. That's when it turns around, when its velocity is 0. So those would be the things I would really want you to do here. This is what you would get the points for. Yeah, you could graph, I suppose, your velocity. You could graph the position function. Some people did that. They graphed the position function, and they saw that at 0, the position function was going down. So that meant it was decreasing, so therefore it's going to the left. Okay, that'd all be good stuff, but you'd have to draw that graph. You'd have to make mention of that. But they're going to want to see the calculus part of it. Somehow you'd have to make some connection that the velocity is negative, meaning it's going to the left. They're going to want to see that calculus connection in there. So set the derivative equal to 0, set the velocity equal to 0, and see the times that it stopped. A number line would be a really good thing at this point. Okay? If you put a -1 into my velocity equation here, I get a negative times a negative, that's positive. If I put a 1 in here, I get a positive times a negative. If I put a 5 in here, I get a positive times a positive. So, clearly, and then again we would say this, since from between 0 and 4 the velocity is negative, therefore the particle started out moving to the left. When does it turn around? It turns around at 4 because it changes, the velocity changes from negative to positive, so therefore the velocity, the particle changes from going left to going right. It actually turns around. It doesn't just stop, right? Just because the velocity is 0 doesn't mean it turns around. It turns around because it was going left, now it's going right. It's kind of like the same justification you would use for local max-min. Y prime is in a positive, then changes to negative, therefore the graph is increasing, the graph of Y is increasing, then decreasing. So, same kind of thing. When, if ever, is a particle at the origin? Now again, think about the x-axis here. The particle starts at -6. We just got done saying that it does what then? Goes left. Until when? Till time equals 4. Now, it never did ask you where it turns around, does it? It just said when does it turn around, right? How would we find out where it turned around? Go back to the original position equation and plug a 4 in. Yeah, you can tell where it was. But at time equals 4, it turned around. And it turned around and headed back. Then what? Then what? It just keeps going. It went left at the beginning, at time 0. It went left for 4 time units, whatever. And then it turns around and it comes back to the right, and it keeps going to the right. How do we know it keeps going to the right? Because it never stops again. We already found all the times when it stops. We already found all the times when the velocity is 0. So it never stops again. So once it turns around and goes to the right, it never stops again. So it's going to come back to the origin at some point. So the answer to the question, was it ever at the origin? Yes. When is it? What do we do? How do we find when it was at the origin? Take the position equation, your part A answer, and set it equal to what? Okay? So that's a key. We got to be able to do that. Because I mean, that's probably the number one thing that we have worked on as an application. We can go back to all the chart questions, you know, with number line and max-min, and now in velocity, position, velocity, acceleration, and that connection of how those things go. Guaranteed you're going to see many, you know, multiple choice and free response questions about that. Okay, I want to go on to number 4 and make a mention about the Shanghai situation here that we have. Again, the key element of the Shanghai situation is 2 different ways of doing slope, so I just want to make sure you're on target with this. Now in part A it talks about doing the equation of the tangent line. Part B then it says how far apart, where do you have to be so you can see the tower essentially, but in other words they want to know this distance right here. We're trying to find this distance. Let's forget in part A they even asked for the equation of the tangent line. How in the world can I get this distance? Well, I need to know what this point is, and I need to know what this point is. And if I can know those 2 points, I'm going to know that distance. Well, this point's easy enough. I got the equation of the parabola. How can I find point P?
By setting y equal to 0.
Yeah, just set that equation equal to 0. This is a calculator problem. I can solve it. So I can very easily find that intercept. That's not a problem. What I need here is this point. Well, same thing. I took this equation and set it equal to 0 to find that point. Very easy to do. So if I had the equation of this tangent line, I could do the same thing, right? If I had the equation of this tangent line, I could set it equal to 0 and very easily find that point. Okay? So that's why in part A they said find the equation of that tangent line. Well, this is where Shanghai comes in. The key to Shanghai was what? 2 different ways to write slope. One way to write slope is the slope between 2 points. Well, let's write our points. Well, this is x and y, but I don't want to write y there. What do I want to write?
100 minus x squared.
I want to write this y. That's what y is. So I want to take that equation, which is the points on the parabola. I want to stick that in for the y. What's this point?
0 and 116.
0 and 116. Now, I knew that because the tower is 16. And some people are asking, well, how'd you know that was 100? Well, it comes from the parabola equation. Put a 0 into the parabola equation, see what the y-intercept is. Put a 0 into the y-intercept, you get 100. So you knew this point, you know this point. Now, since we're going to substitute this, and again, I'm not going to do it for you, but since you've got this equation, you put that in place of y, look what you got. You got slope between these 2 points. It'll only have an x in it, right? It'll have one variable, it'll have an x. Do slope between 2 points. What's another way to do the slope of this line? Oh, good. Geez, people have been slow to say that one. That's the key thing we've learned all year long. The slope of a tangent line is the derivative. That's what derivative is. So you do the derivative of the parabola. And that would have an x in it. So now you got 2 different ways to write the same thing, the slope of that line. Set them equal to each other, you can solve it, you can find what x is. If you can find what x is, now you can write the equation of a line. Because what do you need to write the equation of a line, the tangent line? Slope and a point. Well, you got a point. Right? You got the best point of all. You got the y-intercept. That's the best point of all to have on the line, right? That's the easiest one of all. So you got a point on the line, and now you're going to get the slope on the line. So you can write the equation of the line, which can then give you point Q, and away you go. You got everything you need. That's the key. That was a Shanghai problem, which allows you to write the equation of that line. All right. So we'll set aside those packets, and we got a new one for you today. But first, we're going to turn to page 255 in our books. Page 255 in your book. And we're going to work on completing a little bit more here of chapter 4. All right, might as well. Yeah. Might as well leave that on. Okay. You can tell me if my markers are messing up here. Okay, so we are going to, this is section 4.6. All right, what we're going to talk about here is Newton's method for finding roots of an equation. Now, I think it's more named after Newton than actually something that Isaac Newton discovered himself, but he's one of kind of the co-inventors of most of the ideas of calculus, so I think it's more just a matter of being named for him. But this is not something I learned about actually when I took calculus, because we really need, well, let's just say you need some, there's a lot of hand calculations to be done. You know, Newton's method was used a long time ago when that was the only option they had, was a lot of hand calculations. Okay? There were people, we talked about this in computer math, there, you know, before the 1940s, you know, before there was such a thing as a computer, if you looked up computer in the dictionary, it would refer to a person who computed, you know, who maybe did computations for a living. You maybe have seen in science class, I'm sure they have a great big book of formulas, the CRC handbook. You may have seen one of those. Now, you don't have an actual book you have to refer to anymore. Most of that stuff's all electronic and online. But there used to be tables of trig values and logarithms and square roots, and you would, if you wanted to do the square root of 37, you would go to a table. You go to a square root table, and you'd look up 37, and there would be the square root of 37 out to 6 decimal places. Well, that had been hand calculated by somebody. Okay, so that's what they would do. So this is a method of how they would find roots of equations a long time ago. Well, again, in a high school calculus class, we didn't study that. Well, now that we have calculators and now that we have computers, now it's kind of interesting to come back and study this particular thing. For example, when you type in to your calculator to solve a certain difficult equation, we go to the solve feature, comma x, right? We hit enter. Haven't you ever wondered at all how the calculator's getting that answer? No? You just trusted it, right? I mean, how's it doing it? Just some magic? Well, there's got to be some. There's got to be some algorithm. There's got to be some lines of code that are programmed in to do that. And what it's doing is something either Newton's method or something very similar to Newton's method, something along those lines. And so now that it's kind of nice to know that, you know, if you're a computer programmer and you're going to compute something like this, you would have to know about techniques like this so that you could put this into it. Okay, now, what we used to do is our calculus books would typically give us equations that we could solve, right? Like, for example, the quadratics would most of the time would factor, right, if we had to solve. And a lot of our derivatives were pretty straightforward: sine, cosine, pi thirds, pi sixths, pi fourths, that kind of stuff we'd memorized. We didn't get into these other ones that have weird, crazy answers. Now, what we thought were the hard problems is when we had a quadratic that wouldn't factor. Well, what did we have to do? Quadratic formula. So we spent a lot of time doing the quadratic formula on ones that wouldn't factor, because that's how you solve a quadratic set equal to 0. But for cubics, there is no cubic formula. There is no formula for how to solve a cubic or a fourth degree or whatever. So how do we do it? Well, one of the ways that we could do it would be this thing called Newton's method. Now, it's important because think about what we do in calculus. Think about the quiz we just got done taking. What is one of the most important set of points that we look for in a calculus problem? Local max, local min, which happen where? Stationary point, which is where the derivative equals 0, right? So very often are we taking an equation and want to know where it equals 0. Okay, just from that fact alone, finding stationary points. So finding roots of an equation, that's what that is, finding when it equals 0. Okay, so we're going to go through and we're going to talk about Newton's method. Now, first I'm going to show you kind of a graphical way that it works, and it's kind of cool actually, the thought process behind it. And on the quiz next week, remember that no calculator quiz I said it's about concepts and ideas? There will be a question, something about Newton's method, like describe how Newton's method works. Okay, you don't have to do any calculations for it, but you're going to have to know and be able to describe how Newton's method works. Well, let's go through that. So let's say we've got this cubic right here. We're trying to find where it crosses the x-axis, where it equals 0. That's what it would be. Okay. Now, like I said, 150 years ago, they couldn't easily even draw the graph of a cubic. I mean, you could plot some points, but it was kind of tough to do. You would use some derivatives, some calculus stuff, try to find if there's a local max, local min, that kind of thing. See if there's an inflection point, where's that at? And if you could draw those things, then you could get a pretty good sketch of it. Okay, but you still couldn't get an exact place where it crossed the x-axis. Okay, so how do we go through it? Well, here's what they would do. We'll start with a guess. So we're going to start with 4. We're going to say, well, let's maybe 4 is the answer, right? Maybe 4 is where it equals 0. How can I check? Plug it in and hope I get what? 0, right? So that's what I'm going to do. So I'm going to plug in 4 and hope I get 0. Oh, shoot, I did. I got 3.59. Okay, didn't get 0. So here's the genius part of Newton's method. Newton's method says, okay, we didn't get 0 that time, but you know what let's do? Here's something we can do. We could calculate the tangent to that curve right now, right? Because we now have the point. And what else do we need to do a tangent line? The slope. Now we can do cubics. That's easy to do a derivative of a cubic, right? Matter of fact, 100 years ago, 200 years ago, they knew all the derivative rules. All the derivative rules have been around. So we can do derivatives of even complex equations. So we can do the derivative, and we can plug in and get the slope. So if we have the slope, if we have the point, we can do the tangent line. So let's do the tangent line. Now, let's find out where the tangent line is 0. Now, the tangent line is a linear equation, mx plus b. Is that easy to see where it equals 0? Absolutely. A linear equation is easy to solve, see where it equals 0. So what we're going to do is we're going to see where that line is 0. And we're going to make that our next guess as to what the root is. And now we're going to repeat the process. Okay? So what I did is I said, hey, I didn't know how to solve a cubic where it equals 0, but I do know how to find a linear equation equals 0. I'm going to use this idea of the tangent line. So I'm going to repeat the process. So I'm going to plug that in. See if I get 0. Oh, shoot, I did. Okay, well, I'm going to do the tangent line there. I'm going to see where that crosses the x-axis. Okay, and I'm going to plug that in. Maybe that's working now. Maybe that's the right one. So I'm going to plug that in, see if I get 0. No, but look what I got, 0.24. Getting closer, right? And now I'm going to draw that tangent line. Now, remember we talked about locally linear? Like if the point of tangency is really close to that root, that the points on the tangent line are pretty close to the same as the points on the curve, right? And think about any curve when it crosses through the x-axis. Wouldn't the tangent lines kind of be pretty close? If you got in close enough, the tangent lines should shoot down pretty close. We're going to call that riding the tangent line. I think that's what your book says, riding the tangent line. So Newton's method can be described somewhat like this. Start with an initial guess, plug that into the curve, take that point on the curve, ride the tangent line down to the x-axis. And then do it again. Take that point on the curve, ride the tangent line down to the x-axis, and keep repeating that until you get closer and closer and closer and closer to the root. Now, that was a lot of hand calculations for them to do all that. Okay? Find all those, points, find those equational lines, solve them. Matter of fact, they were smart about it. They made up a formula. They did not just solve the tangent line every time, because that would just take forever. Okay? So let's go through an example, or let's show you how they did that. So this would be worth writing down. We're going to come up with a little formula here. So we've got some function f of x, and we want to see where that is equal to 0. We want to find its roots. Okay? So the first thing I'm going to do is I'm going to find f prime of x. Right? I'm going to need the derivative. Okay? And I'm going to let x sub 0 be my initial guess. Okay? I'm going to call x sub 0 my initial guess. Instead of doing it for, a guess of 4, and then plugging that in, getting the point, and then getting the slope, and then doing the tangent line, then solving that, and then getting it. Let's do it in the abstract. Let's do it in the general case, and let's just see what happens. Okay? So there's my initial guess. So we want to write the equation of the tangent line. Okay? Now what's my point going to be? Well, I'm going to plug in my x sub 0, and the output will be f of x sub 0. Correct? That'll be the point. That'll be the point on the curve. And then the slope will be f prime of x sub 0, correct? So that'll be the slope. All right, so let's write the equation of my tangent line. So my tangent line will be y equals, now what's the slope? F prime of x sub 0 times x minus x sub 0, parentheses, plus f of x sub 0, right? We're doing this in the general case, in the abstract. So we've got our slope, which is f prime of x sub 0, and we've got our point, which is x sub 0, and f of x sub 0. And I want to know where the tangent line does what? Equals 0. I want to know where the tangent line crosses the x-axis. So I'm going to solve this for what variable here? X. So I want to know what x value the tangent line crosses the x-axis, right? So I want to know an output, what x value gives me an output of 0. Okay, so this is easy to do. I can move the f of x sub 0 over here. Now you're only going to have to do this one time. We're not going to have to do this again, but I want you to see where this comes from. It's important that you understand. Okay, so that's going to be negative f of x sub 0. Right? Then what? Divide by f prime. So negative f of x sub 0 over f prime of x sub 0. And then add x sub 0 over. Now when I do that, I'm not going to add it over here on the far end of it. I'm going to put it in front of the fraction because I've got the minus, that negative there, so I'll make a minus. So I'm going to write x sub 0 minus f of x sub 0 over f prime of x sub 0. Let me see how I did that there. Now, and then what is that I just found? But that's my next guess. That's my next guess. So I'm going to call that x1. Right? That's like, so x sub 0 is my initial guess, then x1 would be my next guess. And then how would I find x2? Do the same thing. And so that's a pretty simple little formula there, actually. So Newton's method, so the formula for Newton's method is this. In general, we'll say x sub n plus 1, right? That's like our next guess. N plus 1 would be our next guess. Is going to equal our previous guess, x sub n, minus f of x sub n over f prime of x sub n. That is the formula for Newton's method right there. It's pretty simple, really. All right. Now, there are two ways you're going to be required to work this. Okay. Now, the really, really long way to work this would be what I was saying before. Pick a point, actually plug it into the function, get that point, plug it into the derivative, get the slope, write the equation of that specific tangent line, solve it equal to 0, find your new guess, and then repeat that. And that would take a long, long time. Okay? So I'm going to give you a shorter way to do it, and then I'm going to give you a really, really short way to do it. Okay? And all along the way, we're going to get to use our calculators to help us. Okay? So we're going to do this example right here. All right? We're going to, let's take the example of f of x equals x squared minus 2. Okay? F of x equals x squared minus 2. Now, I like doing this example because this tells us actually a couple of things. Where are the roots of that? Where are the roots of that? No. Close. I mean, negative root 2 and 2. Root 2, right? Plus or minus root 2, right? You set this equal to 0, add 2, square root both sides. Plus or minus root 2, right? Now, because this reminds me of something also that we used to do with square roots. Again, before, when I first learned about square roots, even the little calculators were not that common. They were expensive, and the 4-function calculators were around, add, subtract, multiply, divide, but a lot of those didn't have square roots. So I remember when I was in middle school, to learn how to do square roots, we had to work them out by hand. And so to do a square root problem, we would do this. We'd say, okay, first we called it the divide and average method. Okay, the divide and average. Anybody ever done this? Have to do this by hand? The divide and average method starts with a guess. So you say, well, we'll start with a guess of square root of 2. Let's say it's 1.5. And so you would do this. You'd say, okay, 1.5, I'm going to divide that into 2. Because what should happen, if 1.5 is actually the square root, what should happen here? You should get 1.5, right? If it was actually the square root. So we would divide it out. And these were in the days when we spent a lot of time doing long division. So we would move the decimal over. 15 goes into 20 one time is 15. Bring down to 5. 15 into 50 goes 3 times is 45. Got a 5, it's going to repeat, right? 1.3 repeat. So I didn't quite get it. But I do know that the answer has to be where? In between those two. So we would average 1.5 and 1.3 repeating. So let's just call it 1.4. And then we would do it all again. And so we'd go 1.4 and divide that into 2. Right? And you might get 1.41 or Or maybe you get 1.42 something. Well, now it's between 1.4 and 1.42, so you'd guess 1.41, the average. And you would keep doing it, and then you would keep doing it until you got to whatever degree of accuracy you were asked for. If you wanted 3 decimal place, you would keep going until you got 3 decimal places, and so forth. It's called the divide and average method. Now we also had table. Oops. We also. You get it? All right. Now we also had tables. We also had tables to find the square root of 2. You could just go look it up, and we could do that too. But we had to do a lot of that stuff. All right. Well, this would be another way. This is kind of a roundabout way, but this would be another way to get the square root of 2. Now, it takes a little higher level. You wouldn't do this in middle school because you got to know about derivatives and everything else. But we could use Newton's method to get an approximation for square root of 2. Because what I did is just invented a function that I knew had square root of 2 as a root. Right? So if I wanted square root of 5, I could do x squared minus 5. Right? Because I know the root of that is square root of 5. So anyway. So we want to solve this equation, or we want to find the root of the function x squared minus 2. All right, well, the first thing I need then is f prime. So we're going to do f prime. Okay, which would be 2x, or you can use your calculator if it's more complicated than that, but we should know our derivative rules anyway. So we got that. So what we're going to do here is we're going to make a table. Okay? So this is the shorter way than doing a bunch of different tangent lines and having to solve all those. This is shorter than that, but it's still going to take a little bit of time. All right. So in our table, we're going to label this column x sub n. And we're going to label the next column f of x sub n. Okay? Because if you think about it, these are the steps we would go through. First, we plug it in to see if we get 0. Because if we get 0, we're done, right? We found the root, all right? If we don't, we're going to write the tangent line. Well, what do we need? We need a point and a slope. So we already got the point, so now we need the slope. So this column is going to be f prime of x sub n. And then I need my formula. Now I'm going to break my formula into 2 columns. First, I'm going to do the fraction. Well, we've got both of those values, so we've got f of x sub n, and I'm going to divide that by f prime of x sub n. So in this column is basically going to take the second column divided by the third column. I'm going to get that. Now again, 100, 200 years ago, these were all things easily done. You could plug into the functions, get those values. You could plug in, you could multiply now by hand, or you had to look up in tables, so it wasn't easy, but that was all they knew, and so that's what they did. And then the last column is going to be the final step of the formula. It's going to be x sub n, which is going to be the first column, minus this fraction, which is the fourth column, and that will give me this column, which is the final thing. And then whatever answer I get here then goes where? Back around to the first column as my next guess. Okay, so we're going to guess that the root of this is 1. Some problems, they tell you an initial guess to start with. Some problems you're going to just make up your own. Okay? Now, on the take-home quiz on Monday, that I give you on Thursday that's due on Monday, you will have one problem where you're going to do Newton's method, the long, well, you can call it the long way if you want, the table way. And one of your homework problems today, you have to do the table method. Okay? Then I'm going to show you a really short way where we can use our calculator. And on the take-home, there'll be a problem where you get to use that shortcut with the calculator. And then on today's homework, there's ones where you get to use a calculator as well. Okay, so the first thing we're going to do is plug that into the function. Now let's right away, let's let our calculators help us here a little bit. So everybody get your calculators out. Get on the calculator page, calculator screen. And this is the quickest and fastest way I think to do this, and that is, let's go ahead and define these 2 functions. So type the word define. We could go into the graph screen and call them f1 of x and f2 of x, but let's type define f of x equals x squared minus 2. And then when you hit enter, it should just say done. So type define, and everybody make sure you get logged in here because I got a document to send you here in a little bit too. Is everybody logged in? Who's not logged in? Ryan, why aren't you logged in? Seth,
Yeah.
you logged in? Log in for me.
I need a hat.
Chris isn't here.
I'm taking it off.
Ryan, go ahead and put a hat on it and log in here. So when I go to send the thing, it'll send. All right. So let's define f of x to equal x squared minus 2, and let's define g of x. I mean, I don't care what you call it, but let's define g of x to be the derivative 2x. Okay? So we've got them in there. They're defined. Okay? So now, to get column 1, or excuse me, to get column 2, you're going to want what? On your calculator. F of 1. So now all you have to do is type f of 1. And you get, now I realize some of these at first they're so easy to be faster, just do it in your head. But at some point we're going to start getting really long decimals, and then it's going to be nice to have it on the calculator. Okay, for the next column we want g of 1, right? F prime of 1. What do you get there? 2. Okay, what do we get now? We're going to divide those. So now again, once we get our decimals, now you can arrow up. You can arrow up and grab them. So we want to take column 2 divided by column 3, negative 0.5. And then what's the last column? We want to take this minus this. First column minus the fourth column. And you get 1.5, right? And then the 1.5 is our new guess right there. So now you've got that 1.5 set there, so now you want to repeat it. So now we want f of 1.5. Now, I don't care. If you want to do 1.5 squared minus 2 and do all that, that's fine. But this, I think, shortcuts a little bit. What do you get? How much? 0.25. Okay? And now this would be g of 1.5, right? The derivative. 1.5 plugged into the derivative. 3. And now we'd have column 2 divided by column 3. 0.083. Root 3 is repeating, okay? You want to write down a number of those decimals. Now, the nice thing is you'll have them saved on your calculator, and you'll be able to go up and grab them. Because you can get off pretty quickly with rounding error here if you use rounded values. We don't want to do that. Okay, and then finally we take column 1 minus this, and we get 416 repeating. Okay, which is now our new guess here. Most of the time on these problems, depending on your guess, you're going to have 3-4 rows. Probably I won't make any that it probably goes much beyond that. But okay, all right. So now we want f of that number.
00694.
2 zeros, you said. Okay, and then g of that number, or f prime actually. 2.83 repeating, and then those two divided. Okay, and then finally column 1 minus this one. Okay, now what is the square root of 2? Go ahead and do it. What is the square root of 2? Okay, so we're already accurate in the third decimal place according to what the calculator says. Now, we'll go ahead and stop right there. And the problem will tell you 3-digit accuracy, 5-digit accuracy, whatever it wants, okay? And you'll just go to there. But now let's talk about how do you know when to stop. And also, the reason I make you do the table, because there's a couple of interesting things in the table. First of all, this column. What's important about this column? What would we like to see in that column? Well, even better than that. 0. I mean, we'd be great, right? If we did this column and got a 0, we'd be done, right? That number would be it, because that's what we're looking for. I mean, so again, let's don't lose the big picture here. We're trying to find the root of this. We're trying to find when the output of this is 0. So if we get a 0 in this column, that's great. We're done, okay? But for the most part, we want to see it getting close to 0. So when we see it getting close to 0, we know we're getting close, all right? And then this slope column doesn't tell us too much, but this is an important column too. What's that column give us? I mean, that column's getting small also. Well, it makes sense because you're taking this. It's the accuracy, isn't it? Because think about what you do with this column. You take your previous answer, 1.4166 whatever, and you subtract the 0.00245 number. Well, when you subtract, everywhere you see a 0, what's going to happen? The number won't change. That means those numbers are right. Those numbers are correct. So this tells us right here, even before, now you don't need this column. You can just look at these two answers and say, hey, they both have 1.41. I know I've got 2 decimal places of accuracy. The third place has changed, so I don't know what the third place is, but I know I've got 2. But actually, I knew that before I ever did this column. I knew it right here. Since I had 2 zeros there, I knew the number I was about to get in the last column was going to be accurate to 2 places. Now, if the question said 3 decimal places accuracy, you'd have to go one more step. So you'd have went one more column, and we might have gotten 3, might have got lucky and got even 4 decimal places of accuracy on the next step. Okay? Because sometimes it jumps like that. But these 2 columns really are kind of important. They kind of tell the story of what's going on there. All right. So, again, the genius of Newton's method is using the derivative, using the idea of writing the tangent line and local linearity. That is that the tangent line, when you get the tangent line close to that point, that the tangent line and the curve are pretty much the same. And we use the tangent line to solve it, and it's this process that gets us that formula. So I want you to really understand that this is just not some made-up out-of-nowhere formula. It came right from the equation of a tangent line, set equal to 0. But yet everything here is pretty accessible by just some add, subtract, multiply, and divide. Which, again, several hundred years ago they could do. It wasn't a lot of fun having to do it by hand all the time. But they could actually find these values. Okay? So that was one of the techniques that they'd use. Well, now that's programmed into your calculator. This kind of thing is programmed into the calculator. And so that's one of the ways that it can find these solutions to these equations when we ask it to solve them. Now, not every equation you put in is set equal to 0. But actually, can't you make any equation set equal to 0? Right? If you got this stuff equals this stuff, just move all this stuff over to the other side. And then you've got it equal to 0. So you can always turn any equation into a function set equal to 0. Or an equation set equal to 0. Okay, that's the table way of doing the Newton's method. And you're going to have to do that on one of your homework assignments and on one of the take-home problems that we do. You're also going to be required on the next quiz next week to describe how Newton's method works with this idea of writing the tangent line. Now let's look at a couple of instances where the tangent line runs into some issues. Okay? For example, let's take this sine curve right here. Okay? Now let's make our initial guess right about here. So we put that point in there. Now, anybody have any thoughts about what's going to happen? Or any thoughts if I move my initial guess over to here? Because what's going to happen next? We're going to ride the tangent line. Now, there are a lot of roots to the sine function, right? Now, my guess is if you guessed in here, you're probably hoping to find this one. Well, where's that tangent line going to go? We talk about riding the tangent line. It's going to shoot you way over there. Now, let's move it back to where I had it here a second ago. Move it back a little bit farther, like so. So let's say we started there. Well, now when we go to our, wait, too far. Okay, so now when we do our tangent line, it takes us over to there. Okay, that's our next guess. So now let's plug that point in. Get the tangent line? See, what happened was it took us, the blue tangent line shot us clear past this peak. So our next point, now our tangent line shoots me over to here. Which skipped a step. Gives me that x-intercept, which gives me that point, which now gives me this tangent line. Okay? And now I don't have enough steps to go through here, but I can move this. This is kind of cool. Look how wildly different that is with just small adjustments. Your book talks about that being the butterfly effect. You ever read anything with chaos theory? And there was a movie, I think, called The Butterfly Effect. That was well, it's a little bit the same kind of thing. With the butterfly effect, basically says a butterfly flaps its wings in Nebraska, causes a monsoon in China. You know, small changes in one place end up making big changes in their place. So a little pebble into a pond, and then and then the ripples go out, so forth. That's kind of the butterfly effect. That's where it gets the name. But that is a kind of what's going on here. Very small changes make a big difference. Because look, right here, the blue tangent line shoots me over to here. But if I would have just made a little better initial guess, now the blue tangent line shoots me down to the x-axis here, which then gives me this point as my next guess. The green tangent line comes back to here, then the red one comes back to here, and eventually I would zero in on this point right here. Okay? We'll look at those here in a minute on the shortcut way of our calculator. That's the best way to investigate these different things. Okay, let me show you one other. Now, the book refers to that as a shallow tangent. See, look, here was the issue. My initial guess, when I made my initial guess up here by the peak, okay, when I made my initial guess up here by the peak, I have a real shallow tangent. Well, if I ride that tangent, it's going to take me a long ways to get to the x-axis. Matter of fact, what if I had a horizontal tangent? What if I picked exactly at the peak? It would never go to the x-axis. Well, look at your formula. What happens if you pick the peak? The derivative would be 0. It'd be undefined. It wouldn't work. So a shallow tangent, it's not that it won't find the root. It's just what your book says is going to find the wrong root. It'll shoot your way out and it'll find a root maybe not near the one you wanted to find originally. Okay? Here's the last thing on this, and then I'll show you the calculator shortcut. This, your book refers to as cycling. Now, this doesn't happen very often. It'd have to be almost a wildly unlucky thing that this would happen. You'd make a guess. I guessed here at 1. Now, it's not exactly 1. It's off in the 100th decimal place, so this isn't going to look exactly perfect. If you look in your book, there's a picture of this on page 261. If you look on page 261, this is what I'm trying to replicate here. But I wanted you to actually see it. But if I make a guess at 1, and I look at the tangent, okay, it goes over here right through just about 3. Then I do the tangent at that line, and it takes me right back to the 1. And then I would do that point, and then the tangent would, now it's off just a little bit, so it actually makes a difference, so it doesn't. But the picture of the book shows it better. And so if you would actually get a 1, and then a 3, and then a 1, and then a 3, and then a 1, you would never zero in on a root. No pun intended. Okay, so you would just cycle back and forth. So those are a couple of the issues that can happen with Newton's method. But for the most part, it works really good. So let's go to your calculators, and I need a volunteer. Nah, we'll just pick a volunteer. Oops. All right. Who did we get? Chase. All right. All right. So Chase has already got his things defined in there. So let's go ahead and do the, now everybody do this on your calculator as well, because this is the really cool shortcut right here. So the first thing you would do is go into define f of x and define g of x. All right? Now, we're going to go through the same thing we did in the table here. All right? So the first thing Chase is going to do is type in a 1 and hit enter. Okay, now what we've done is we've just seeded the calculator. There's something on your calculator. If you look at the negative key right next to the enter key, in blue above it, it says ANS for answer. That's a variable that stores the previous answer. Well, if you think about that, that's going to be really nice here, because that's exactly what we do. We take our previous answer and then we want to plug it in again. So what we're going to do now, so what we've done is put our 1 into that variable answer by doing a 1 and hit enter. So we do that to start. What I want to do now is I want to take that 1 and I want to plug it into this. But I don't want to type a 1, I want to use the variable answer. So I want you, Chase, to type, hit control and that negative to get answer, minus, now I want to plug answer into the f function, so I'm going to type f of answer. He went ahead and got the fraction, which is good. So type f parentheses and then answer. And then down here we're going to want what? G of answer, because G was our derivative. Now this is really cool, because now before you hit enter, okay, I want you to think about this, because what's going to happen is you're going to get fractions, not decimals. So always do, at least to start, at least until you get a decimal, hit control enter. So he hits control enter. Okay, now stop right there. He got the 1.5, but here's the real power of this. The calculator always remembered the last thing that you typed in. And so when you hit enter again, it will redo the last thing you did. Well, the last thing he did was answer minus f of answer divided by g of answer. Except what's in answer now? 1.5. Hit enter. See that? Hit enter. Okay? So it's a one-time, you just type it that one time, and there they are. So 1.5, 1.46 repeating, 1.414, okay? And then you can just hit enter a couple times, and pretty soon it would agree in all of those decimal places. Right? See, at some point they don't even change anymore, because you've got it accurate out to those decimal places. Okay? Now, let's do the one we did with sine. So, Chase, I want you to type in define f of x to equal sine. Sine x, yeah. And then, of course, g of x will equal, so you got to define g of x to be the derivative then. And again, if it's faster, just let the calculator do the derivative. Most of the time, it's going to be easier just to do it yourself. Cosine x, the derivative of sine. Okay? All right, and now we're going to start it with a 1.3. So we're going to type 1.3 and hit enter. And then we're going to do that answer thing again. You can't go up and grab the previous ones because they actually have numbers plugged into them now. So you have to go answer minus f of answer. Now you could do it. I didn't think of this. Is there a copy and a paste somewhere?
Yeah, control C and control V.
Okay, so when you get f of answer and now put g of answer, before you hit enter, go ahead and highlight all that. No. Oh, how do you highlight something? Arrow up. A quick way is arrow up, and arrow back down. I'll try it again.
You have to hit enter before.
Oh, maybe, okay, tie out. But there is a way to do this. Okay? Hit the right, hit your right arrow right now so you get to the far end. Hold the shift, which is that, where's the shift? Right above the 7. Hold the shift and now hit the left arrow. Hold the shift and then left arrow. Keep left arrowing while you're holding the shift. Oh, whoops, you got it. There you go. And left arrow all the way. It's kind of like a click and drag. Okay? So a shift and left arrow. Now go Control C to copy. So we can really get lazy here. Okay? All right, so we go ahead and hit, now make sure your cursor gets past it now, or get it so it's not highlighted. Now hit enter. Okay, now notice, 1.3, that took us a long ways away from where we thought we were. Remember when I did the sine one and it took us way off to the negative side? Go ahead and hit enter again. Enter again. And what root's it finding? Enter a couple more times. Negative pi. Sine does have a root over there at negative pi. It found that one. Okay, let's do one more. Chase, go ahead and define f of x to be this function. Okay, ready? Okay, here it is. X cubed minus 6x squared. Whoops, you're up in the cursor. Up in the, there. Minus 6x squared plus 7x plus 2. Okay? And let's define the derivative to be g of x. Do your derivatives right in front of everybody. Oop, it should have been 3x squared. You need to square it on the 3x. Oop, 12x. You had it right last time. You had the 12x last time. Okay? Alright. There you go. Now let's seed it this time with a 1. Put a 1 and enter. Now let's see if this copy and paste thing's worth. Go Control V. Control V. Oh, awesome. Hit enter. Enter. Oh, God. Enter. Okay, that's the one from the book. It just goes 1, 3, 1, 3, 1, 3. So that's what's happening. Your tangent line's going over to here, and then down the curve, taking you back to where it started, and it's just cycling around. Okay? All right. So, your homework. There's going to be some problems in the book. You've got half an hour or so. You can probably get those done. Pretty close to done, I would think. And then we've got some stuff in the packet. Okay? So, everybody look on, follow with me here on page 261. Now, I think this is on that assignment sheet. It's only 3 problems, so it's, I think you can, yeah. The problems are going to be 3, 5, and 15. Okay, now let me describe to you what you have to do on 3, 5, and 15. On 3, they give you, if you're on page 261 with me here, they give you a picture of that function, and then they ask you, if you started with an initial guess of 0.95, which of the roots would it converge to and why? And so you're just going to answer it and give an explanation of what's going on. Okay? Turn to page number 5. Number 5 gives you a function. They tell you they want you to look in the interval 0 to 1. So 0.5 might be a good starting point for your guess. And they want you to find the solution to 3 decimal places. So number 5, I want you to do this table. Okay? Question 5, I want you to do the table. All right. 15, they give you a function, and they say it's got 3 roots. They want you to find all 3 to 5 decimal places. I want you to use this shortcut here that we just talked about. Now, if you want to graph it to get an idea where they are so you can get some initial guesses, I'm okay with that. But I want you to practice going through this shortcut. All right? So that's part A. Then part B says, what happens if you try a 2 as your initial guess? Part C says, what happens if you guess a 1.39? And I want you to be able to explain what weird thing's going on and talk about it. Okay? So question 3 is just kind of what's going to happen in that one. Explain it. Question 5 is this table. Question 15 is this shortcut we just did on the calculator. All right, in the new packet, you should try to get as many of the multiple choice as you could. Like I said, if you work hard here, you can get the book part probably done. So, you know, the first 28 are the no calculator ones. Maybe try to get those done. You know, the more you work ahead, the better off you'll be on these. But try to get as much of the multiple choice done as you can. That's your assignment for tomorrow. So 3, 5, and 15. 3, 5, and 15 in the book, and a bunch of multiple choice questions in the packet.
See? Sign up
Oh,
later,
it's
70.
45.
Well, you only have 6 hours.
There's still this.
Don't do
that.
I was like, oh, they're not front and back.
Okay, stay logged in because towards the end of the period, I'm going to send you a document that you can play around with Newton's method a little bit on the calculator. So I'm going to send you that later. So stay logged in.